So I begin my talk will be about a little introduction to what I call a global singularity theory. So let me write this. Let me see if it works. Global singularity theory. Let me explain what the problem is. So let's just see an example. The idea is the following. We have a map between two manifolds M and N, and so I look and we'll consider a particular regime. So the regime is when we have the dimension, which I'll denote by M here, and here the dimension, which I'll denote by N. So we'll look at the regime when this is less. So we look at smaller dimensional manifolds mapped into larger dimensional manifolds, and interesting question. So what first definition or first object is the case of immersions. So when a map is an immersion, so the definition is the following. I can take point P in this manifold M, and then the image is Fp, and then we have a map dF, a linear map from TPM to TP, TFP N, right? And so the immersion, this condition of immersion, means that this map is injective, or if you like, the rank is M. So these are the, that's the definition. So what we'll be interested in, if we take two manifolds M and N, in this, say, if we fix the homotopy class of the map from M to N, if there are immersions in it. So that's the question. So let me just give you a quick example. Say, let's look at the RP2, which is just the two-sphere with respect to, by identifying the antipodal points. So am I supposed to look at the chat? Yeah. Yeah. And so the question is the following. I will be looking at maps from this space into R3. And the question is does there exist an immersion? Does there exist an immersion? Okay, so I will not answer this question today. I'll leave you to look this up, but this is quite a reasonable question, and I will describe now an approach to how to deal with a certain aspect of this question. In fact, the approach will tell us how to prove that the immersion does not exist, in fact. Okay, so let's go to our next point. So the point sort of obstruction to existence of immersions, so obstructions. And at this point, because it's more convenient, although I'll make a remark about the real case later, but for now, I'll just pass to the complex case. So the manifolds are complex, and of course, then the category of maps is holomorphic. So I'll pass to this case. And so the obstructions to the existence will be done using characteristic classes. So the idea is we have a manifold M, a vector bundle. So our manifold M, a vector bundle V, and then we can define a series of classes in H, in the cohomology of M, starting with just C0 of M, which is just 1, and then there is C1, it's V. C0 of V, then there is C1 of V, etc. And then there is CR of V, where R is, say, the rank of the vector bundle V. So the idea is roughly of these classes that we look at generic sections of the vector bundles, and then this CR of V, for example, is just the gamma equals 0. It's the 0 section of this section, and this wiggly thing I just mean here. I just mean that it's homologically equivalent. It's Poincare dual, in fact, to this section. Okay. So we will try to use these homologic classes to describe the obstructions, and so we'll introduce generating a finite generating series of these classes. CT of V will be just the sum T to the J Cj V, J going from 0 to R. And then given our setup, so this setup here that I have up here, I'll just maintain for the rest of the talk. So it's the two manifolds with the dimensions fixed. This will always be there. And so in our current setup, then we can define the following thing. We can then look at T of the pullback of the tangent bundle of N, and also just the total Chern class of the tangent bundle of M, and we can look at its quotient. It does make sense because it has values in a nilpotent ring, and so this definition will define this as the characteristic classes, which is now formally an infinite series of our map F. And so indeed, this class that we introduced here now, this total class, only depends on the homotopy of F. And so this will be our language for proving that finding the obstructions. So let me give you the answer to the question of how, or a partial answer at least, to the question of obstructions to the extent of immersions, and this is the following. So it's a theorem. We can call this the Theorem of Portus. And it's the following. So let's introduce now that locus, the locus of the singularities of our map F. And so it's just defined again as those points for which the rank of DFP or DPF is less than M, so it's not a full rank. And so this is a definition, and then the statement is the following: that if F is sufficiently generic, which I will maybe comment on a little bit later, then this sing F is in fact say Poincare dual, or it's equivalent to the following thing. It's Cn minus M plus 1 of F. Okay. So this is our first result, and so we are looking for results of this. So of course, so now this produces the obstruction I was talking about, because if we now look, so the obstruction, of course, in particular, this implies the following thing, is that if we have Cn minus M plus 1 F is not equal to 0, and now as an element of the cohomology of M, that means that in this homotopy class, there is no immersion. No immersion in this homotopy class. Oops, like that. Okay, so this is the language of our approach to the problem. So this problem was solved, and actually it has a very simple answer, as I described here. So the problem is, of course, that singularities of maps are much more complicated. By the way, so when I talk about global singularity theory, I always mean singularities of maps. Okay, so in particular, this sing F, this space, is in fact is stratified in a very complex manner, and I'll now describe this stratification. So there's actually many ways of this, of classifying singularities of maps, and I'll just introduce a particular one, which turns out to be probably the best way of looking at this. It's not the finest classification. So it's the following. It's this classification is called contact singularities. And it's the following idea. So again, of course, the setup is the same. I have two complex manifolds M and N with a map F between them, and now I'll define an invariant. That's the first step. So let's take an arbitrary element, and now let's define the algebra of this space, sort of the local algebra of this map F at this space, which at this point, which is the following. So I just so this is the definition. I just look, well, very schematically, is just O of P divided by the ideal generated by the pullback of O of Fp. But I'll make it more explicit in the following way. So what this is really the following. So this is just looking at, say, power series in m variables, 1 xm. And what I mean by this, so, and then dividing it by, so maybe, let me start it describing what I'm doing instead of giving the final definition first. So the idea is the following, that I'll take local coordinates and I describe the map in some explicit way. So I'll take local coordinates both around the point P and also around the point Fp. And then the function f at the near our point may be described as a set of equations. So y, say, j, which is just some power series. So these are the coordinates in the coordinates x1, xm, and we have j goes from 1 to n here. So this is just a local description after fixing local coordinates. Okay, and so now once I have this, then I can describe the local algebra in the following way, that I look at the sort of the local ring. So these are just x1, xm, the local ring of the functions on the space M near the point P, and then I quotient this by the ideal generated by these coordinate functions, right? Okay, so that's the local algebra. So it's a basic theorem that if say if near P we have an emergence, so in particular if that df is sort of the implicit function theorem, if this d pf here that I was talking about at the very beginning here, if this is in fact injective, this map, then the algebra will be maybe trivial. So every local function near the point P on M can be represented as is in the ideal generated by these functions P1 up to Pn. And if it's on the other hand, if the function is singular, then this algebra will at the point P, then this algebra will be non-trivial. But now I refine the singularity locus with respect to this algebra. So let's formalize this. Normally in a generic behavior, since our dimension m is less than dimension n, so now this algebra will be finite dimensional. So let's fix a finite dimensional algebra with some extra properties, not so important now. And then from this, we can define this singularity locus. We can refine the singularity locus of F, as we defined before, by looking at those points P in M, for which this algebra at the point PF is isomorphic to A. Okay, so this is now a refinement, a partition of the singular locus with respect to this local algebra. Okay, so now if I have just a second. So the simplest series, actually, this is the problem I'll be describing is already very, very complicated for very, very simple algebras. So I'll introduce a series of algebras, say A, D will be just CT divided by T to the T plus 1, this finite dimensional algebra, for example. Okay, so for example, if I say if I look now, so we define, we'll look at this series. So if I look at, say, sing A0, so these are just the immersions. And if I look at sing A1, so this is when the algebra is basically the algebra of dual numbers. So this is the simplest thing. Well, of course, these sets are open, but once I close it, then normally this will be, for a sufficiently generic case, this will be just the singularity locus of the function f. Okay, so these are just some examples. But if I look at, say, A2, then this is already a relatively complicated subset. So what we are interested in is to understand the following question now, replacing here just the condition of singularity, I will try to identify the obstructions for avoiding singularities with local algebras, which are, for example, A2. So this would be the generalization. And this is somewhere where René Thom's program of classifying and understanding singularities of maps starts. Okay, so let me now formalize the result of formalize the language first, in which we are looking for the answer of these abstractions. So these are this I'll call this the theorem of Tom and Damon. Tom, Damon. And it says the following. So what it says, it posits the existence of certain universal polynomials. So it just says that there is an answer to our question in the language that I introduced here, and for which we already found an answer in the very simplest case of the A1 singularities. So let's see, well, let me just say this. So it says the following, again, for, this works actually for any algebra A. So let A be finite dimensional algebra. Then there exists a polynomial which I'll just denote by TH for Tom. It's called the Tom polynomial. Just two parameters. So of course it depends on this algebra A, and it also will depend, in fact, only on the codimension of the map. So it's the dimension of the image minus dimension of the source space. And so the arguments are, and I'll just put some dummy variables there, are just C1, C2, etc. So it's a polynomial, of course, it's homogeneous to describe the Poincare dual to what we want to get. And it's a polynomial such that, in fact, our Sing for F generic, sufficiently generic, we have that the singularity with this algebra A of our map F is, so this locus, well, I'll close it, so it's really, you get a variety, and then its homology class is in fact equal to THAN minus M, and we simply substitute for the dummy variable CJ hat the actual relative characteristic class, relative Chern class of our map. So the claim is, the theorem is that it exists, and it only depends on such polynomial exists. So that's the key. And it's for every generic map, it actually defines the locus. And of course, then again, if you want to prove obstructions for the non-existence of maps avoiding a certain singularity, then we just need to evaluate this polynomial and see if this polynomial then is zero or not in the cohomology of the space M. Okay. And so from here, the challenge, and it's essentially a challenge in enumerative geometry, is to calculate these polynomials. And this is very, very difficult. So Tom started his works on this were in the 50s, and then during the 60s and 70s, rather, there were several results calculating these polynomials for certain algebras or for certain types of singularities. But really, this progress stopped very, very quickly. So let me just describe, it's the first, maybe the only really impressive result from the 70s. That's the formula of Runga. So I mentioned that the next non-trivial case. So let me give you an example of a calculation of this Tom polynomial. It's the formula of Runga, Felice Runga, my colleague, Runga's formula. It's the following. So it's just the formula for the Tom polynomial of the A2 case. And it looks like this. So so again, I take the Cn minus m plus 1 that I had for Portus's formula. Now, of course, it's much deeper, so it's the codimension is greater. So it's squared. Then you have Cn minus m multiplied by, so there's a hat here, right? So Cn minus m plus 2, and then plus. And so it's basically, then you just get sort of this obvious sequence of monomials where you have, they are all quadratic in these C's, and the sum of the indices is always the same. And the coefficient is just powers of 2. So it's 2i minus 1 of Cn minus m plus 1 minus I, and Cn minus m plus 1 plus I, and plus etc. So it's formal and infinite series, which again, of course, stops because if one of these indices is negative, becomes negative, I mean, it's this one is going to eventually become negative, then the series stops. Okay, so this is the formula of Runga. So it has this feature that is kind of double graded, it's quadratic in these C's, and the sum of the indices, well, that's necessarily, of course, is equal to the codimension of this variety, saying A2 for the case of A2. So this was a promising result, but then it's basically stopped calculating it. For example, for A3 was completely impossible. And it's only in the 2000s, then 30 years later, there was sort of a not completely maybe explicit result obtained by a group of researchers, Rimanyi and collaborators, and still this problem remained open for a long time, even for A3 and certainly for A4, etc. There was a big progress made by Rimanyi in the early 2000s, I think. Rimanyi's restriction method, which allowed to calculate various coefficients in this series. So while his solution for various algebras was not complete, but this gave some important partial results and also ways, of course, to check any calculations that you would make. So it's difficult to explain why it's so difficult. I mean, you should try it, of course, but roughly speaking, I mean, it is the problem with this is that it's enumerative geometry, or maybe one could say that it's GIT, geometric invariant theory. Roughly speaking, this problem is related to geometric invariant theory, where the group is not reductive. So the group is roughly the diffeomorphous group of the circle or of the line, or more complicated diffeomorphous groups. But basically, it has to do with GIT with respect to diffeomorphous groups, and this is very, very, very difficult. So that's why even the Mumford's revolution in GIT did not really lead to a big progress in this area. So now next I will describe my work, my joint work with Berczi, where we found not complete, but really we could say a solution to this problem. At least we translate it into some other language which gives a complete answer in lots of cases. Okay, so let me now go to the formula. So this is work by Berczi and my Berczi. There's an R. I should know this. Berczi, myself, and after we found our results, in fact, it was rethought and recast in a much better form. Some very deep insight by Maxime Kazarian. And this is now for the case A equals, thus AD equals to this algebra that I was talking about. So let's try to see what the obstructions for avoiding having points with this local algebra in a map are. Okay, so it's a rather complex story, so I'll try to describe the answer. So that's now the purpose. Okay, so I'll try to describe what form the answer has. But you will see, so the idea is that what I'll describe at the beginning is simply there should be a piece of the answer which only depends on this algebra A. Okay, so I'll describe that, and then I put this into some machine, some washing machine, and then the result comes out. Okay, so let's see that. So that is the following. Maybe one little remark I make right here. Remark is that, of course, in fact, as I said, there are some conditions, but here it's very clear, is that this algebra AD has a filtration, right? So it's a D plus one dimensional algebra, which has a filtration by natural filtration by polynomials whose degree is at least something, right? So if you have sort of the lowest degree term is quadratic, for example, you have two quadratic polynomials, at least quadratic polynomials, so ones that do not have linear and constant terms. When you take their square, then then they'll be at least degree 4. So it's a filtered algebra. And so we'll use that because that cuts down the dimension of the story very strongly. So I'll denote this filtration it's a temporary notation by nabla. Okay, so nabla is a filtration on CDE on a d-dimensional thing. So it's not going to be d+1 dimensional, I'll make it d-dimensional. So what I mean is that I'll eliminate the constant term, and I'll just reproduce now this obvious filtration, but without the constant term, okay, because it's more convenient. And so it looks like this. So it's C. So this is equal to, if you like. So this is CD is just equal to C1. And then here, so those are the at least linear functions. Then these are the at least quadratic functions, etc. And then, of course, you go until at least degree D polynomials in one variable. And then the last one is t+1, which is 0. So this structure you have on AD, but now I'm going to separate it out. The point is that now AD is basically a structure on this filtered vector space, which is a product, right? So you can multiply. So basically, we'll think of this AD as an algebra, as a multiplication structure on this fixed vector space, filtered vector space. And so let's now formalize this. So I'll define a space now of 3 tensors. So I'll denote just by prod, say. So D is just our permanent index now. And I put this little sign there, marking that I'm only looking at products which are consistent with this filtration. So these are just maps, pi mapping from sim2 of this vector space, of this filtered vector space, and mapping into CD. Okay, so and I put a little thing there, which doesn't mean that it's that map. It means that this map is consistent with the filtration. So as I described, so if you take something in the filtrum 2 and multiply it by another one in filtrum 2, you should end up in filtrum 4. Okay, so these are symmetric products consistent with the filtration, but this is just a linear vector space now. So these are not necessarily really products. They are just maps consistent, 3 tensors consistent with the filtration. And now I'll define a subvariety here. So these are these contact subvariety corresponding to AD. And this is just those products, pi, which induce on CD, because I define the product, an algebra structure, which gives you an algebra structure on CD, with which CD becomes isomorphic to AD, or AD divided, well, AD reduced, so I eliminated the constant term, so AD bar, so with a reduced AD. So again, I look at the space of products, and then inside that space, I look at the subset which actually gives you an associative, of course, commutative product, which is isomorphic to AD. So that's this variety. So this is actually not so trivial, this subvariety, but still for small values of D, the situation is very, very simple. Okay, so let me just, but first, before I describe this variety C, let's just look at this prod for small values. So let's just look at, say prod, well, let's look at the simplest case. So prod, so which one is the simplest? So let's look at this space. So prod 1 is completely trivial. So the first non-trivial thing is prod 2. So when I look at the A2 case, and here the point is that the dimension is simply 1. If you think about it, if you take, I mean, what is the only non-trivial possibility if you only go until degree 2 is that you take the product of two linear functions, which turns out to be quadratic. That's the only possibility. You don't have any other things. Now, if you go to 3, then you'll have slightly more possibilities. I think the result there is 3. You can have product of two linear things is quadratic, product of two linear things. So let me write that. Dim prod 3 is equal to 3, right? So you have the product of two linear functions is quadratic or cubic, and a product of a linear and a quadratic function can be cubic. All those are the only 3 possibilities, and so those give you dimension 3. So for small values of d, this is small. Of course, when it grows, it still grows cubically in d, the dimension here. Okay. So now I will introduce, I will not define this very precisely, but I'll use the main object that we need to derive from this whole thing. And this is the following. I'll call this, so for this, I need to just introduce one more piece of notation, which I'll just do a different color because it's a bit crowded here. So I'll define this toric action toric diagonal action on this vector space CD, and I'll introduce the weights for this action. So now the weights are, well, they're not quite Z1, Z2, etc., ZD. Okay, so but what I mean, of course, is that Z1 acts on of course, C1 divided by C2, of course. So these are one-dimensional lines, and Zi acts on the corresponding one-dimensional line here. So these are just, I denote them by weights, and now actually this will become very similar to what to the notation. In fact, you will see even the notion that Maxime just spoke about a few minutes ago, except my z's here, z's were actually the variables, and my z is actually the weights acting on these variables. Okay, so I have this toric action, and so in this situation, it's clear that this variety, sorry, just one point. This variety C is, of course, invariant under this diagonal toric action. And so in this situation, there exists a notion that we are interested in. It's the following. It's called multi-degree, and I'll define QD, which is equal to the multi-degree, mult-deg, of our variety CAD as a subset of a vector space, of our vector space prod D, like this. Okay. So this multi-degree is a generalization of degree, and it's basically defined for vector spaces with toric actions, and these are where we introduce notation for the weights, and what you need is that it's defined for invariant, torus invariant subvarieties of these vector spaces. Okay, so I will not define this precisely. At the degree of QD, the one thing to know, so the point is that QD, so there's two things. QD is a polynomial of degree, polynomial of Z1 up to ZD of degree equal to the codimension of the corresponding variety. Well, in this case, it's just CAD. Right? Okay, and so let me just give you some examples. So say Q1, this is of course trivial, so here it's 1, but it turns out that Q2 and even Q3 is equal to 1. Okay, so it's really a very, very simple case, even for the D equals 3 case, which, as I said, was not actually completely understood even before our work. But then you can look at Q4, and that will be Z1, it's 2Z1. 2Z1 plus Z2 minus Z4. And here I can maybe just explain a little bit of what this means very vaguely. The following thing is happening. So so the meaning of this this multi-degree is to describe sort of how this variety lies in this vector space, in this affine space. And so the way, essentially describes the degrees, the multi-degrees of the relations, you know, of this variety CAD. And here in particular, you can sort of understand what is happening. So you have these formal products, and for the cases d equals 1, 2, and 3, this does not impose any conditions. Every formal product is actually an associative product. But for the case, the first case is d equals 4. This 4, there is a condition, which is the associativity of this product. And this is actually, if you look, is precisely the degree of the associativity condition. It just means that if you multiply sort of 1, 1, and 2, so it's a linear quadratic, then you should this you can do it in 2 different ways, and then you get something in the fourth philtrum. And so that's 2 degree 1 and 1 degree 2 leads to degree 4. That's where the associativity relation in fact lies. And so then you can calculate Q5 by hand and Q6 with the computer and Q7 with a very, very, very good computer. And then Q8, we don't know how to calculate. So it's difficult to calculate, but of course the Tom polynomial also becomes enormous then. But let me now get to the main formula, the formula of the Tom polynomial, and it looks as follows. So this is now the answer. So our theorem, and it just says the following, that the Tom polynomial of AD, and here we take the n minus m, and it looks as follows. So try to save space here. It's so let me see. Yeah. Okay. Well, I'll need a whole line for this. So let me just come here. So we do the following. I start by constructing a simple rational function, and the rational function looks as follows. We start with a Wundermann. So this is just zi minus zj in this variable z, and for I less than j. And then I multiply this by QD, this polynomial that we just calculated in z's, and then I divide this, and here I just give you the list of all the weights of this vector space P, prod d delta. Okay, so for example, for the beginning, for the Q equals 2 case, you will have, well, I'll give you some examples. The weight is 2z1 minus z2 because you have, so this one-dimensional case, because you take 2 linear functions and you can create a quadratic one from it, and that one-dimensional space has weight 2z1 minus z2 in terms of these weights acting on CD. So those are the ways I'm going to give the list of those weights. And the condition of preserving the filtration just says that this is a product of of these weights. So I take something in the ith philtrum, then multiply by the jth philtrum, and I have to be sure that it ends up in the lth component in the lth philtrum. And the only way that can happen if I plus j is less or equal than L. Okay, so and of course everything is at most D. Of course, so this is d. Okay, so I construct this rational function, and basically that's it. Now I just have to extract the answer from this, and it goes as follows. So here I just have a as sort of a standard factor. So for each of these z's, I introduce a copy of our. So I'll write it now in terms of ZL, and it's, well, I write, these are these C's, you remember, with the hat, but I already make the substitution. I multiply this by the codimension. And then here, well, I prefer to think of these as differential forms because then you can take residues, but I'll actually make an algorithmic definition. So these are just generating functions with a shift of the same f's that we had. But instead of t now, so I have this infinite sequence here somewhere. Let me just go back, sorry, so to show you where we were. Here, instead of this t, I substitute there the variable 1 over z to the power j, or L, or I don't remember. What did I use here? I haven't used anything yet. No, I used L. So that's just an index. Okay. And so I have now this big rational function with values on indices with values in our characteristic classes, where this letter byte is a standard thing. And then what you need is the following. You just look at the, you expand this in the region where, so just like you here see it here, ZD is, well, it actually will go the other way because I look at infinity. So it's 1 over ZD is going to be smaller, but so here it appears as larger, like that. So you expand it here in the region as Z 1 less than, oh, sorry, not like this, Z2, etc. ZD. So make this expansion. So what this means algebraically is that you just divide here by ZL because it's bigger, and then you make an expansion as a geometric series, and then you just take the coefficient, and then you do this expansion, you multiply everything out and take coefficient of the product of BZL divided by ZL. Okay, once you make the expansion. Okay, so it's sort of an expansion at infinity. That's why you have this 1 over ZL. So that's the answer. So this is a truly beautiful formula. You have here these weights coming from our variety, this QD, this multi-degree, which can be calculated easily for small degrees of D. And then here you just have the generating function of our standard series with the codimension entering as a shift in the formula. Okay, so that's the result. And now I just want to make a quick remark before I go to my second theme, is about the geometry. So of course I'm not going to be able to explain the proof, but the sort of the central geometric object is the following: is that we have the Hilbert scheme. And this is not really very surprising, in fact. It's the following. So I look, I'll take a local part of M. So I look at the Hilbert scheme of D+1 points in CM. Okay, so which are just, right, it's just the ideals in R, which is a notation I introduced for polynomials in our M variables. Those are those local coordinates that we had before of codimension D+1. Right, so this is the Hilbert scheme of D+1 points. And well, we'll need to go to a part of this. So first there is here the Hilbert scheme of D+1 points CM. So this 0 means supported at the origin. And then there is the so-called curvilinear Hilbert scheme. And this is supported at the origin. And of course, this Hilbert scheme comes with with a universal, like a Grassmannian, with a universal algebra, which is just a universal vector bundle, which is R mod I. And it just says that this algebra R mod I is isomorphic to AD. Right. So this is sort of these are sort of rather standard objects, and it's very well known if you ever thought about it or read about it, that this is like an infinitely complicated, terrible thing with lots of components, and it's not equidimensional. And even this is horrendously complicated and has many components and not equidimensional. But this is a reasonable thing. I mean, this is sort of what we are interested in, and we are going to be working on this. And in fact, what is happening is that is roughly the following. I just can give a little indication, is that what we're doing there up there, you remember with these P1 up to PM, these polynomials, which are elements in R, R to the M, I guess, such that the ideal generated by them is isomorphic to this AD. So this was, if you remember, sort of the local in the definition of the local algebra, and this algebra now is specified to be AD. Then, in fact, quite obviously, we have this is fibered over this C Hilb 0 D plus 1, because of course, if you have roughly what the data here is an element of exactly of an ideal. It's precisely this thing which has the correct quotient algebra, and here we specify some generators of this ideal. In fact, so there's just additional structure. So you have this fibration, and essentially our result is integration. So that our result is an integration formula. Integration on this Hilbert scheme, the curvilinear Hilbert scheme. Hilb 0, and it's integration of some tautological integrals, just like you have for the Grassmannian for this tautological vector bundle. Okay, roughly that's the result. And so now in the remaining time, I will. So I don't know if there are any questions here. So I've finished this part. And I'll just go to the other part. So in fact, there is an other shoe in global singularity theory, which is not exactly singularities, but so this other shoe is the multipoint formulas. So let me write it in blue, multipoint formulas. But the setup is exactly the same, but we're interested in a slightly different question. And what makes this more difficult, that this question now is not quite local. It cannot be determined just by knowing the function in a neighborhood of a point. And that's why it's much more difficult. So roughly the statement is the following, there are various technical issues, but roughly it's the following, that in the same setup at the beginning, I now define a multipoint locus where K, so now it will be K is the number of points, a multi has one parameter K. This is of the function F, and this is just those points in M for which there exists Q1 up to Qk minus 1 at different points in also in M, such that F of Qj is equal to F of P. So basically, these points P needs to have brothers, at least K minus 1, different from, of course, also different from P. Brothers or sisters who have the same image, right? So this is the multipoint question. It's again the same issue. Can you avoid having multiple points with certain multiplicity in this case? Okay, so that's put it differently, we would like to calculate the class of this variety. So this is again a subset in M, and we are interested in the fundamental class of this variety for a sufficiently generic element, generic function. Sorry. Okay, so here it turns out that it's a little easier to define the thing the class of the image of this variety in N. So the question will be the class of F mult K F, which is now N. So it will be a class, that the class, in fact, will be in the cohomology ring of N. Okay. The codimension, by the way, it's easy to see. The codimension is equal to K times N minus M. And so this is has a long history, and particularly in the 80s, Kleiman wrote a long series, series of papers on calculating partial results on this thing, on calculating this class. And then there is just some absolutely stunning result of which I'll call the Kazarian Rimanyi conjecture, which actually gives the answer to what this should be. And the class has the answer has the following form. So we'll look at, so let me call this class just as a matter of notation as T mult. Okay, so it's not Tom polynomial, it's Tom multiplicity form, if you like. You'll see why, actually. So it's the following T mult, okay? And so, of course, well, I need to fix the codimension. And now this should be a set of classes defined here on the image, okay? And so it's the following thing. So these will be some universal formulas again. Well, there is an inclusion formula. So it's actually what you need is to partition the indices into some parts. So this is a little less important. So S J S. Yes. So I take a partition and then you take products for some polynomials S. So this is just well, it's not minor, but that's not the key. The point is that these polynomials, I'll give a formula for this polynomial S. That's the key point on which the result is based. And the conjecture said that this S L is equal to simply, so it's going to be a push forward because that it should be a cohomology class in N of the Tom polynomial, and with just slightly shifted indices. So I'll have L minus 1 here, and I'll have, instead of N minus N, I'll have N minus M plus 1. So in fact, the multipoint formulas are given by exactly the same results as exactly by the same formula as before. So I need to stop. Maybe I have 1 or 2 minutes. So this, of course, is a completely stunning result again, because there are many partial cases that were calculated. So let me just give you the first few cases. So say the case where you just have sort of 1 point, and then of course, so that's just the image of M in N. So this should be just the push forward of 1. And then if you look at the multi-point formula for F lors should be for 2, then you should have squared plus F lor star of C N minus M of F. And maybe let's just make 2 little remarks here, and I'll stop there. So the point is the following: is that so the problem of calculating it, if you do it the very naive way, is that you look at M cross M going to say N cross N, and then essentially what you need to do to calculate the multipoint formula is to intersect the, so let's call this F2 F2 of M cross M, the image, you need to intersect it with the diagonal. This is N here, so edible N, with the diagonal in N. And the problem is that in there you have the diagonal of M as a subset, and it's an excess intersection. It doesn't have the right dimension for the intersection. So that's roughly what you need to do. And so you need to, so if you just did the usual naive thing, you would get this term, and then this is a correction term for this excess intersection. So roughly that's the problem. And this factor here is precisely the thing, according to the Kazarian Rimanyi conjecture, is precisely the element that comes from which comes from Portus's formula. So there's the 2, and there is the Portus's formula. And if you go to the very beginning, excuse me, then you can see that it's precisely N minus M plus 1. And so for a D equals 1. So D equals 1 gives you this, and the corresponding formula all the way at the end, it's K equals 2, and instead of N minus M plus 1, you have N minus M. Okay, and so just at the very end, so it's work in progress. I think we are now very close to proving this formula with Gergely Berczi, so this is work in progress, and it is based on a special technique of integrating. So again, integrating these tautological integrals, classes, on this Hilbert scheme that I introduced here just a minute ago on Hilb K of, well, here you need to take M of K points on M, which is a very complicated space, but so, well, this is where the work is, but so I need to stop here. So I thank you very much.
Thank you very much.
Okay, so thank you for your talk. By now, I resume my role as a chair, as my computer has at last an internet connection. So there is a question about the Hilbert scheme. You have denoted C Hilb. So the question by Balazs Chandrai is this Hilbert scheme known to be a nice space? Is it irreducible?
Yes, of course. So this one is actually very easy itself. So this space here, the C hill, the curvilinear thing, yes, is of course is just an affine bundle. It's smooth and it's an affine bundle on projective space. Of course, the difficulty, but there's several. The main is that already in our original work, of course, it's not compact. So you close it, and that thing is already, of course, it's irreducible, but that thing is very complicated. So it was an amazing feat that we managed to prove a localization formula on the compactified version, on the closure. So we have a partial understanding on it. For example, it's an amazing formula that in fact we look at the fixed points of the action of the torus action on this space, and then in fact we don't know how to give the list. We have a proposed list of, say, fixed points, and you do that, and we don't know which elements of the list actually are fixed points or not, roughly speaking, but we still managed to calculate by some vanishing theorem, prove that only one of the fixed points contributes, and then that's somehow how the proof goes. But so it's really, the space itself is easy. The closure, of course, is irreducible, but is already motivically we don't know how to describe. But there is a way to prove a localization formula for it there. Now, in this latter case, of course, the claim is that there's a different localization formula which localizes the integral we are trying to calculate on this horrendous space onto this same space, of course. I mean, because the claim is that it is this where am I here? So that it reduces to this AD Tom polynomial for some amazing reason. So roughly speaking, what's behind this geometrically is that, so this Kazarian Rimanyi conjecture is actually means that somehow this integral that we can write on the big Hilbert scheme, it localizes near this curvilinear one, I mean, format. So this is some non-trivial thing.
Okay, so as I know very little in this on Hilbert schemes, I have a naive question. Does the global singularity theory say something about the geometry of Hilbert schemes or of some Hilbert schemes? So I just have the idea that it is extremely difficult to say something on Hilbert schemes, except for the fact that in general they are projective schemes. I am talking about Hilbert schemes classifying subvarieties in some projective space. Okay, so but even for instance, to know the connected components, to know the irreducible components, even in particular cases, is extremely difficult. So at least I think that, maybe I'm wrong. So does the global singularity theory allow to say something about that?
So I think the situation is as follows. So as I try to not hide it very deeply, this fact that of course we cannot really say very much about the global structure of this really complicated space. And even in this punctual case is roughly, we cannot say much. What we can do is the following. We can take these pieces and we can say things about other pieces, not necessarily this algebra. We can take other algebras, so we can fix a different algebra. And then again, we can say something about the corresponding pieces of the Hilbert scheme. So with these pieces, we can say something. And I think where the biggest input is from, or the interaction is as I just was saying, is about the closure of these pieces. So where the open pieces are well understood, the closure which lies in this Hilbert scheme there, that structure is still very, very deep and complicated, even though the fundamental class, of course, is the same. And that thing, there is an interaction. I think for globally understanding these components, etc., we cannot do anything. But this is what's called these geometric components. They are called of the Hilbert scheme. There is an interaction.